Let me know when you're ready.
Yeah, we're good.
All right. So we are at our last meeting for the academic year for the Chester County Astronomical Society. It's been a great year. Again, my hat's off to Bruce for being such a fantastic program director this year, giving us great programs. Seriously, a lot of work and hard effort goes into that. I know because I did it, and I did a lousy job compared to what Bruce is doing for us. And
the checks in mail.
So again, it's been a fantastic year. I really enjoyed every single program that we had. There wasn't a stinker in the bunch of them. And it's been a fantastic year of growth for us too. We even have, I think, from Westchester University, some students who are hiding in the back of the room there. But welcome to the meeting. You guys, all of you are welcome to come to our meetings at any time. Okay, and especially welcome to come to our observing sessions. So let's kick off the meeting. We have a couple of things we'd like to get underway before we get to our regular speaker. Don is going to give us a little bit of what's up in the sky for the month. And Bruce is going to talk about a little something that NASA has just come out with, which is their 10-year decadal survey about what the priorities are going to be for NASA missions coming up in the next decade. So, Don, take it away.
All right. Turn my camera around here. There. All right, first thing I do want to see, where's my share screen? Okay, I want to talk about upcoming events real quickly. Next Friday, not this Friday, next Friday, we're at Brandywine Red Clay Alliance. And there's some Girl Scouts coming out. So I'll send an email out about this, but anyone that can come out to help, it'd be nice to have people come out. It's like not a big group, and they're I think in 4th or 5th grade, if I remember right. I can't be there, so we'll need to have someone come out to help if we can. So but I'll get an email out about that. And then end of the month, Memorial Day weekend, Saturday the 28th, we're at Hoops Park. And this will be our first time back in 3 years. So, and then we usually have anywhere from a dozen up to like 25, 30 people come out. So we'll need people to come out, even if you don't bring a telescope, come out and just hang around at Hoops Park. It's a nice location. It's not great for the sky, but it's not bad. We have a pretty good southern view. So those two events coming up, we'll begin around sunset for both events. I do want to do a slide on camping events because we have a couple of camping events coming up. York County Star Party is near the end of June, and that's only about an hour drive from Westchester. So even if you don't camp, you can go down for an evening and come back. It's not, again, it's not a wonderful site, not like Cherry Springs, but it's a lot of fun. When you're in a camping field with about 24 other astronomers, it's always a fun night. It really is. Pete was there last year, Dave was there, and we had a few others came down. This is the big one for me. Barb and I are going to this. We're not going to York County because the next week is Green Bank Star Quest. That is an amazing event. Several hundred people attend. It's camping or there's also a bunkhouse at the world's largest fully steerable radio telescope. And it's in the middle of nowhere. And that's on purpose because there's no radio waves allowed. You can't have no cell phone service. And even microwaves are not allowed unless they're in a Faraday cage. So you have to Google that. But and then we have 2 camping events for the club at Cherry Springs, which is every bit as amazing sky, if not better than Green Bank. And so that's the end of July, the end of August. Both of these are around, of course, around the dark sky window. And another York County Star Party in September. I'm going to try to go to that one. And that's also at Susquehanna State Park, which is on this side of the Susquehanna. So it's not that hard to get to. All right, so that's what's coming up. And let me mute some people here. So let's take a quick look at the night sky. Let everyone can see this at home. Let me change the lights a little bit. Because it's hard to see in here. Does it look okay?
Yeah.
Anyone been out observing lately? I'm going to turn this around to see the crowd. Last night? Yeah, we were last night. Yeah, we had Dave did a wonderful job presenting the telescope class to our equipment class to our night school students. Some very, very engaged students. There were 8 people out, I think. And about 6 or 7 of them came out to observe in front of Henderson High School. The moon was stunning. We saw the lunar straight wall, Rupert Recta. And we're out there, what, 45 minutes probably with them? About an hour observing. And the moon's all we look at over and over and over. It was great. Really had a lot of fun. Other than that, there's not been a lot of observing going on. Of course, we got rained out last weekend. I think everywhere on the East Coast got rained out because it was astronomy day. And there were all kinds of events scheduled. Everything got canceled with the storm that came through. So tonight there is again a stunning moon in the sky. We're past the straight wall. I always start looking in the west because what's going down. So here the Gemini twins heading down. This is your last shot to get at the 3 open clusters in Auriga. These are all a lot of fun to look at. Center on this one. They're all a little different. So it's nice finding all 3 of them. M37, M36, and M38. But in the sky, they all have a little different character. And they're not terribly hard to find. I mean, you can find them with binoculars if you sit down and take your time and use the Kathy B style of laying back and hold your binoculars above you and looking up. So worth taking a look at them before they head even closer to the horizon. A beautiful open cluster. I looked at this, I think it was Friday night 2 weeks ago. I was out looking at M35. It's a big cluster. And it's another binocular cluster that you can see it in a telescope. Beautiful cluster. I was working on the Messier program for the Astronomical League, and I was searching for M38.
Thank you. Forget your phone.
Pete, please mute. If you're on Zoom, please hit the mute. Be quiet. I got it. The M48, another big cluster, open cluster. Even in the light polluted skies of Westchester, like last night we were talking with the class, what do you look for? Well, planets, the moon, and open clusters. You can see an open cluster in almost any light polluted sky. And M48 was very nice looking. Even when it was getting close to the horizon for me, it was not hard to find. And surprisingly, one of my favorite spots in the sky, of course, the moon was not out last Friday. My favorite spots in the sky was here at the tail of Leo. And even in light polluted skies, I got 2 out of 3 of the Leo triplet. The Hamburger Galaxy, which is this one, I couldn't quite get, but I could get M66 and M65 in my big binoculars. So you can even see galaxies. We're what, a mile outside of downtown Westchester. So even around here on a good clear night like it was Friday a week ago, not last Friday, you can still see some good stuff. Other things to look for. Right here is a nice open cluster. It's a huge open cluster. This, you can barely get this coma cluster of binoculars. It's that big. It's really a smudge in the sky. So for those who are new to this, maybe this is Stellarium. It's a free program. It's easy to download, easy to work. And just Google Stellarium and you see up here. And it's a great program. So now a great time of the year is coming, the spring here. This is globular cluster season. And here's probably possibly the grandest of all in our skies is M13. This is probably 500,000 stars, maybe a million. I don't think anyone really knows. But can you imagine living on a planet around one of those stars? It would get dark at night, but there'd be a lot of bright stars in the sky. There's another one up here. Oh, really? M92 is not quite as big and showy, but also a very nice open globular cluster. Other things up here. This is what I wrote about in the newsletter recently. This is Kuma. This is a double star. Double stars are a lot of fun. They sound like not that interesting, but they really are interesting. This one's called the cat's eyes. This is New Draconis. And I never tire looking at the cat's eyes. They're interesting because they're close, but there's decent separation. And the magnitude of both stars is almost identical. So they're really, really nice looking. Look like a pair of eyes looking down at you. And not too hard to find. If you can find the head of Draco the Dragon, this guy here, you can find Kuma. Another wonderful one at this time of year. If you take this line in the scoop of the Big Dipper and extend it out, you can get, I'm going to cheat and use the search rather than poke around. M82. Oop, other direction, sorry. You can find M81 and M82. You can get these in one eyepiece of a telescope. And it's a nice contrast. We're seeing one of the galaxies sort of on the side and the other one to the face. So these were called Bode's Nebula because before we knew what galaxies were, everyone thought these were nebulas. They thought there was only one galaxy, ours, until Mr. Hubble, of course, instructed us that there are galaxies all over out there. Any questions? Those are the things that I'm usually looking at in the sky.
Early morning at about 4 o'clock.
Yes, there's some amazing stuff going on. In fact, I will go to that time right now. Have you been up to see it, Dave?
Yep.
About 4 o'clock or so?
The cat gets me up. She wants to go out.
Let's go to the east.
Drag the telescope in.
There we are. Yeah, there's some wonderful sights in there. If you can get up that early, if your cat gets you up, Venus, Jupiter, Neptune, Mars, Saturn is
Off to the right.
off to the right yet. Okay, there we are. There's Saturn. 4 naked eye planets visible early in the morning. A rare sight. So truth be told, I wish we had them in the evening sky, but so, we will, yep. Okay, any questions on anything up there? Kathy?
Not about that, but about, I think last year you did, or you did, I wasn't there, street astronomy? Like,
That was it'll be 3 years ago this September.
oh my gosh.
Yeah, we did sidewalk astronomy in Westchester,
Sidewalk
and we're going to
astronomy.
try and set that up again. I have to just take my iPad out to the courthouse, the historic courthouse, and set up the make sure pick the right night.
Yeah.
But I've been talking with Westchester Recreation. They're up for that.
Good.
I just have to nail the details down on that. Yeah.
Good.
Yep. That was a blast.
Good,
Yeah.
yeah, wasn't able to go to it. That's
Yeah,
why I
it was a
thought
blast.
it
We
was.
had how many? 150 people came through that night.
Easy.
Yeah, it was amazing. It really was.
In various states of inebriation.
Yep.
Well, Friday night in Westchester, I forget it.
That was happening.
Okay. I think Bruce, you have something, right? There, Mike's just coming on now. Good. Why don't you come on up, Bruce, and okay. All right.
So hi, everyone. Welcome again, as Dave said, to the last meeting of the year. And before we introduce our speaker, we just wanted to take 5 minutes and mention a report that came out last month. It's called the Decadal Survey, or the full name is Origins, Worlds, and Life, a Decadal Strategy for Planetary Science and Astrobiology, 2023 to 2032. So what this is, it's a once every decade report that is released by experts from the National Academy of Science, and they make recommendations for what are the major questions or issues facing planetary science and what kind of missions NASA should undertake to address them. So This is not binding for NASA, okay? There are major recommendations and they prioritize, and then they recommend optimal levels of funding, and NASA then takes these under consideration. So just to mention, this year's report was pretty important because the highlights are the major recommendation and highest scientific priority for NASA's robotic exploration in the next 10 years should be the completion of the Mars sample return mission underway by NASA and the European Space Agency. The second major recommendation was the development of an orbiter and probe to Uranus as a flagship mission. Maybe you know or not, the only mission that has ever gone to Uranus was, I think, 1986, Voyager 2. And there's a lot of interest in knowing more about, this gas giant. And so that's one of NASA's highest recommendations. And that was followed by the recommendation for an orbiter and landing mission to the moon, Enceladus. Again, you probably know we have the Europa mission going, the Yankee Clipper mission going to Europa. So this would be sort of the next generation mission. And then importantly, for the first time ever, this survey recommended a very strong effort and funding for NASA's planetary defense efforts. This is something that NASA spent $0 on not that many years ago, and now they spend a couple $100 million, I think, annually. But what the real focus of this would be is that NASA build or complete its near-Earth observing telescope that would be dedicated specifically to look for near-Earth asteroids and other objects that could cause obvious problems for us all. So those were the major recommendations, along with what is now underway, the Artemis mission to go back to the moon. Those were the major findings, and the recommendations for funding on this were also quite substantial. Kind of a base level of recommendation was $35 billion over the next 10 years, but the optimal level of funding to support those priority missions would be in the order of about $41 billion. So that's almost twice what the recommendation was on the last decadal survey that came out, in 2012, which was like $22 billion. So again, these are not, they're only recommendations from experts to NASA. NASA usually takes them under quite careful consideration, but they don't have funding attached. That's up to state policymakers and government. So I just wanted you all to know this. I think it's pretty important. So stay tuned for the next 10 years. So with that, I'd like to introduce our speaker for tonight. I'm really excited about our speaker is Dr. Michael Brown from Caltech. He is the Richard and Barbara Rosenberg Professor of Planetary Astronomy. He's been faculty there since 1996. And for those of you that don't know, Mike is an expert on trans-Neptunian bodies. In the Kuiper Belt, he has discovered many dwarf planet objects, and probably unflatteringly, he's the guy who's credited with killing Pluto as a planet, okay? In fact, he actually wrote the book, How I Killed Pluto and Why It Had It Coming. So we won't hold that against him. But I mean, he is a clearly renowned astronomer. He has won more awards than you can imagine. He was inducted into the National Academy of Sciences in 2014. And I believe about 8 years prior to that, he was on Time Magazine's list of one of the 100 most influential people. So we're really pleased to have Mike here. And what Mike has been working on for a number of years with colleagues is the search for the elusive planet 9 in the outermost regions of our solar system that, if it does exist, may be accounting for some of the gravitational effects that are impacting a number of trans-Neptunian objects, many hundreds of AUs from the sun. So without further ado, we'll turn it over to Mike. And again, Mike, thanks very much for joining us.
Thanks. It's my pleasure to be here.
Hey,
Just
Mike,
so, yeah,
give me 1 minute. What I'm going to do, I'm going to turn the camera around.
that's,
so
I was just about to say, can you turn the camera around?
we have about a dozen or so people here. We have 5 watching us on YouTube, and we have, let's see, we have about a dozen or so, more than that.
I can see all of you. You look
Yeah,
very small.
We have 18 on Zoom.
Okay.
So
I see this-
I'm going to I minimize the participant screen for now. If anyone comes on and is making gibberish because they haven't muted, I may have to bring this participant screen back up, but I will try to avoid doing that. And let me get my other screens down here and get you back up to on Zoom.
Okay. And I'm assuming you can see my first slide here.
Let me get this up a second. Yes, let me minimize this. Okay, yes, we can see Planet 9 from outer space. We're good.
Okay. So I'm
Okay.
really happy to be here to talk about my favorite new topic these days, which is this search for a real ninth planet in the solar system, not a make-believe planet like that old one that used to be the ninth planet, but a real ninth planet sorry, it's just the way it is. But to talk about this ninth planet and to talk about the searching for planets in the outer solar system, it's really important to go back and understand the history of searches for and discoveries of planets in the outer solar system. And I like to do this. I was giving a talk on this topic a couple of years ago, back when you used to go places to give talks, and I was in Copenhagen, and there's this tower in Copenhagen that you can climb up into, and you go up this spiral staircase and you get to the top of it. It was an astronomy tower, and there is a clock, which is an orrery, which shows all the locations of the planets in the sky, and you could see them all. There's Mercury, Venus, Earth, Mars, Jupiter, Saturn, and that was it. That was the last planet. This was built in 1775, and there were only those planets. And at that time, as far as I can tell, nobody really thought that there were other planets in the solar system. You know, the telescopes had been invented and had been being used to chart out stars, and everybody knew that there were stars that you couldn't see without using a telescope. But as far as I can tell, in trying to research old writings about this, nobody speculated about the existence of other planets beyond the ones that you could see with your naked eye. And so it's not surprising, I think, in 1780, when William Herschel started mapping out the skies and found this object that looked kind of like a planet. It wasn't a little point source. It was a big smeared object. His first reaction was not, oh, look, I found a planet. His first reaction was, it's, you know, a planetary nebula or some of these other things. He went back and looked the next day, and it had moved. This is, of course, the big telltale. All the stars, all the galaxies are in the same place night after night relative to each other. But if it's something in our solar system, it moves. And this one had moved just a little bit. And by moving just a little bit, Herschel knew it was in our solar system. It was moving in our solar system. He could calculate that it was beyond Saturn. But even then, he was not convinced it was a planet. He didn't want to call it a planet. Other people started calling it a planet before he did. He's like, well, you know, it could be a comet. People knew about comets back then, and they travel on these elliptical orbits and sometimes go pretty far away. And so Herschel was really trying to hold out. But eventually he gave in because, you know, it's kind of fun to discover a planet, I guess. And he decided to name it. He tried to name it George. Didn't stick, but that was his first try. What he really wanted to know, and what everybody wanted to know at the time to decide if it was a planet or not a planet, was, does it go in an orbit like a planet? Which to them meant, does it go in a circular orbit around the sun? Or is it like a comet that comes in close to the sun and goes out much further away? Well, it's hard to know with such a long orbital period. It's hard to know if Uranus is in a circular orbit or not without watching it for a really long time. But this problem was solved by an astronomer in Paris, Alexis Bouvard, who wrote this presumably fascinating book on astronomical tables of Jupiter, Saturn, and Uranus. I know that was probably flying off the bookshelves. So what he did is try to figure out where Uranus was and try to figure out how it was being gravitationally perturbed by Jupiter and Saturn. But the really important thing he did to start with is he went backwards in time. Notice that you can start to see this table over here is observations of Uranus and the dates, the year here. And, it was published in 1820. And so 1819, going backwards, there's many, many observations. People are looking all the time. You get all the way back here to 1782, then a couple in 1781, then 1771, 69, 1750, 1690, something like 100 years before Uranus was discovered. Bouvard went back and found observations of Uranus. Some astronomer somewhere had made a star chart and they placed Uranus, which they thought was a star, on a chart. And Bouvard went back and looked at all these star charts and said, hey, I think Uranus should be around here somewhere. Oh, there's a star there that's not really there anymore. He put it on his list. So the first thing that he did is he allowed himself to have this huge time span of dates for observations of Uranus and proved that it was in a circular orbit around the sun. This was until Bouvard went back and found all these data, it was still not known for sure if it was in a circular orbit. So that was great. More importantly, or as importantly, maybe, he, as I said, he was calculating all these perturbations due to the gravity of Jupiter and the gravity of Saturn. And so it doesn't just go in an elliptical orbit around the sun, but it has these deviations, and he calculated them all and showed precisely where Uranus should be. And well, this second column, you can see errors, it says. And sometimes Uranus is a little in front, sometimes a little behind, in front for a long time, behind of his predictions, in front. And Bouvard, as maybe the preeminent, what we would call him today would be a theoretical astrophysicist. As the preeminent theoretical astrophysicist of the day, he was pretty sure, just like they are today, that his observations were perfect. His theory was perfect. So the observations had to be wrong. So he says this down here in this paragraph. He says, astronomers basically need to make better observations. And then it'll match my theory perfectly. He does say in this last little paragraph that maybe there's an alternative, maybe there's another body out there, but no, mostly it's just astronomers are bad and they need to be better. So people started trying to make better observations. Starting in 1820, astronomers were very careful to precisely chart the position of Uranus and measure it with respect to the stars. And for 20 years, they did this, and it was still in the wrong place. By about 1840, it was widely understood through the astronomical community that the reason that Uranus was in the wrong place was because there is another planet still to be found. Everybody knew this, but people didn't know how to find it. And it took calculations by somebody working at the same Parisian observatory by Urbain Le Verrier, who used these precise data that you're looking at to pinpoint the position of this new planet in the sky. And he sent it in a telegram to the observatory in Berlin. They opened up the telescope, and that very night they found Neptune, which is, to me, this still to me is one of the most astonishing stories in the history of science and the history of astronomy that I don't think people really had wrapped it around their heads before yet, that this physics, this calculus, all these calculations you can do, they don't just sort of let you explain the world around you. They let you make predictions as profound as there's another planet to be found out there, and it's really there. This got Le Verrier super famous. He became known as the astronomer who found a planet at the tip of his pencil. He's got a statue in Paris now, looking straight north up one of the main boulevards. His name is etched on the Eiffel Tower. Super famous. He got so famous that other astronomers realized, hey, finding a planet, that's a pretty good way to get famous. So people started predicting planets left and right. Everybody was predicting a planet. There were the first planet predicted after Le Verrier was literally within months. Somebody looked at the observations of Uranus and the observations of Neptune and said, hey, they're not in the right place. Something else is tugging them along. And I think there's a planet here. And then somebody else said there's a planet here. Even Le Verrier got into the action and predicted another planet, this time inside of Mercury. And by our count, as of a couple years ago when I last counted, there were at least 35 separate predictions of planets beyond the orbit of Neptune due to some phenomena or another. And every single one of those 35 times, the astronomer who predicted it was wrong. Wrong in the sense that the phenomenon that they were trying to explain either was not true, the physics they were using was wrong, or something else was just not right. So it has been for a long time, this has been sort of the folly of astronomers who want to become famous. The most famous, who I guess he did become famous, the most famous of these astronomers who wanted to become famous, who then became famous, was one that we all know of, which is Percival Lowell. Percival Lowell, of course, founded the Lowell Observatory in Flagstaff. He was from Boston. And he was responsible for many of these predictions of a planet beyond Neptune. He was convinced that Uranus and Neptune were being tugged along quite strongly by this massive planet still out there. And he wanted to find it. He tried doing some observations himself, didn't happen, and he passed away before the telescope at Lowell Observatory, which eventually was successful, could get built. But eventually, based on his predictions, they started doing a search of the sky, and Clyde Tombaugh, of course, found Pluto. Because he was looking for a massive planet beyond the orbit of Uranus and Neptune, everybody was convinced it was a massive planet. In fact, if you go to the New York Times headline of the discovery, it suggests that it is possibly as large as Jupiter, but certainly larger than the Earth. This is only wrong by a factor of 250,000. It is not nearly that big, but that's what everybody thought at the time because that's what they were looking for. We now know, of course, that the only reason that Pluto was found in the survey was really just utter coincidence and luck. And if you look at the orbit of Pluto, here's the orbits of the giant planets, Jupiter, Saturn, Uranus, Neptune. Pluto was always this weird oddball. It's on this orbit that intersects the orbit of Neptune, goes inside, comes back out again. And if you tilt the entire solar system on its side, you realize that Pluto, unlike the planets, Pluto is tilted. The orbit of Pluto is tilted with respect to the planets. It never really made sense. And people called it a planet back in 1930, both because they were looking for a planet. They thought it was huge, and only over time did they realize how small it was, but also because it was kind of nothing else to call it. It was the only thing known outside of Neptune. This all changed 30 years ago. I'm actually embarrassed to say it was 30 years ago. I forgot it was 30 years ago. I got a call from a reporter this morning, and she's writing an article on the 30th anniversary of the discovery of the first new object in the Kuiper Belt. I'm like, oh my God, that's 30 years ago. I can't believe it. I was a grad student at the time. I'm feeling old now. But 30 years ago, a new object was found in space beyond Neptune, and then another, and then another, and then another. And as of now, there's something like 3,000 objects known in orbit beyond Neptune. And just like Pluto, they're on orbits that are tilted, they're on orbits that are elongated. Some of them go inside of Neptune's orbit, some of them go outside of Neptune's orbit. They really are all of the same sort of object as Pluto. So Pluto is no longer an oddball at the edge of the solar system like we once thought it was, but clearly part of this population of what we now call the Kuiper Belt beyond Neptune. The interesting thing about the Kuiper Belt beyond Neptune is it gave us the opportunity to have many, many more objects to try to see if we could understand if there were, other planets out there beyond Neptune. And the answer as of 2001, also getting to be a long time ago now, the answer as of 2001 was absolutely not. There is no need for anything else beyond the orbit of Neptune, no gravitational influence. Those perturbations of Uranus and Neptune that Percival Lowell thought he was seeing, they were just bad data. Alexis Bouvard finally got his revenge. Astronomers had made some bad observations, particularly back in the early part of it. And those suggestions that Uranus and Neptune were being tugged along were just wrong. And Uranus and Neptune were in the right place. Everything was in place. Every single object in the solar system, its orbit, its location, everything could be explained by the 8 planets that we know and the sun at the center. This all changed in 2003. It's never any fun when you can explain everything. It's always more fun when something else happens. So in 2003, the fun began, and we discovered a new weird object. And this new weird object was so weird that it doesn't even fit on the plot here. You have to move it all to the side. And this is Sedna. Sedna has an orbit that goes well outside of this region of the Kuiper belt that we were looking at, and takes about 5,000 years to go around the sun. This was discovered nearly 20 years ago, but I hope some of you remember it even way back then. And the funny thing about Sedna is actually not that it's on this super elongated orbit that takes 5,000 years to go around the sun, but that it never actually comes close to the Kuiper belt. That's actually very strange. And the reason it's strange is because what we think happens is that all objects are formed with circular orbits around the sun. We're pretty sure that that's the only way you can form an object on a nice, pristine circular orbit around the sun. And if you're not on a circular orbit, if you're a comet, if you're something like Sedna on a orbit like this, it's because somebody gave you a kick. Everything that's not on a circular orbit has been kicked by something big. And Sedna is no exception. Sedna must have had a very big kick to put it on an orbit like this. The problem is, when you get a kick, you go back to where you got kicked. So let me show you how this works. I'm going to give you a really toy picture of the way Sedna would work. This is the way comets work, anything that gets perturbed in its orbit. So here's the sun. Let's say this is the sun, and let's say this is Neptune. And let's say there's an object that's in orbit very close to Neptune. And that orbit is going around close to Neptune. At some point, it'll get a little too close to Neptune, and it'll get thrown out onto an orbit like this. So it gets thrown out like this, but it always comes back. It got kicked right here. If you get kicked right here, you're suddenly on a new orbit, but that new orbit returns to the place where that orbit started. So it always comes back. It always comes back, which means eventually it's going to go around like this. It's going to get kicked again. Well, it gets kicked again. It's on an orbit that looks like this. What's going to happen? Eventually, it's going to get kicked again. It keeps on getting kicked, and it can get kicked a lot, and it can get a very elongated orbit, but it always has to come back to the spot where it got a kick. Eventually, what's going to happen is it gets a kick and it's gone. This is the way that things get ejected from the solar system. This is the way that comets get injected into the Oort cloud. But eventually, they all go away. And they never end up going like this, getting a kick and coming back to something that's far away from Neptune. The only way to come to a point that's far away from Neptune is not by getting kicked by Neptune, but by getting kicked out here by something else. A simple way to do it would be to have a star going by really quickly that gives you a little bit of a tug in this direction, and you suddenly have a new orbit, and your new orbit looks like this. This is essentially what the orbit of Sedna looks like. It's a long, elongated orbit that never returns to Neptune. And what this means, very clearly, as of 2003, we suddenly knew for the first time that other objects have interacted gravitationally with our solar system, either in the past or in the present or something. But it was irrefutable at this point in time that other objects were in our solar system interacting with stuff. I was pretty sure I knew what the answer was. I was pretty sure it was this star. I actually made this slide back in 2003 to explain this to my class right when we first discovered Sedna. And I was pretty sure that we had uncovered evidence of the formation of the sun in a cluster of other stars. And the way it would work, also made this plot in 2003, the way it would work is that you would have many stars in a cluster like this, and they would slowly tug at the orbit of an object and kind of work its way out and pull it away from the orbit of the sun. And if it worked like this, also suggested it could have been a single star that would do it, or it could have been Planet X, but we all knew Planet X, that's crazy. Nobody believes that kind of stuff. So really what I believed is that this was going on, and that we could find more of these objects like Sedna, and we would really be able to understand, uncover the fossil record of the birth of the sun, which I thought was a pretty exciting possibility. So we spent a decade looking for more objects by Sedna. And in that decade, we found precisely 0 new objects like Sedna, which is really surprising to me. We should have found some. And it took me until the end of that decade to finally realize what was going on and why we hadn't found things. And the way I realized it is we started looking not just at these objects like Sedna. When I say like Sedna, I mean pulled away from the sun. A perihelion is the closest approach to the sun, a perihelion that is not inside the Kuiper belt. We didn't find objects like that, but what we did find is more objects like Sedna, in the sense that they had very elongated orbits. And when we started putting together the list of all the objects with really elongated orbits, we found something peculiar. We found that all the objects we had found with elongated orbits were elongated off in one particular direction. Sedna is one of them. You can find it. It's the only one that doesn't come close to the sun. It must be this purple one down here. See, it never comes close to, the blue circle is Neptune. Sedna never comes close to Neptune. Everything else does. But these objects are all pulled off in one direction. It's a little strange because just like hands of a clock, each one of these objects, it's the direction that its orbit points will rotate with time, and they rotate at different rates. And so the probability of finding them all in the same direction just due to chance is really small. The probability of these being lined up like this was something like 2%. Not zero, but 2% seemed a pretty small number. Plus, if you look at these objects, they're all lined up this way. If you tilt the whole solar system on the side here, it's also peculiar that all of these objects are tilted with respect to the planets, and they're all tilted in the same direction. So all these objects are pulled in one way, and they're pulled up in one way. At this point, I walked down the hall to my friend and colleague, Konstantin Batygin, who's a professor at Caltech. And I was like, what's going on here? This is weird. It shouldn't be like this. Let's see if we can figure it out. And he's a, one of those math eggheads who sits around and does all the equation in his heads. I do all the equations in my eyes by looking at things on the screen like this. He does it all in his head, closes his eyes. And he worked out a bunch of mathematical things. And we were the one thing we knew it's not a planet, because we knew there was not a planet out there. There was no way we were going to be the 36th and 37th people to say, oh, hey, there's a giant planet out there that's being found, because that's crazy. So we were trying to figure out every other possibility. And we spent like a year and a half trying to figure out what else could cause this effect. And the answer is nothing. As far as we can tell, there is no way to get these objects to behave the way they're behaving unless there's a giant planet out there. And we worked out the math worked, and we were trying to decide what to do about it, because the math worked, but it just seemed a little bit crazy that there would be a giant planet still to be found out there. So we decided to try some computer simulations. And these are interesting. I like to show these because they really show you how this behaves. You can barely see it here. This little red circle in the interior, that's Neptune, the orbit of Neptune. This is the orbit of a planet that we put in there. And each one of these blue ovals is a test particle, a test object in the Kuiper belt that we put on a very elongated orbit in all directions to see what happens. So if you did have a giant planet out here, what happens? And what we thought was going to happen is that the planet would kind of capture objects into this little region inside of its orbit, and everything else would get ejected, because crossing the orbit of a giant planet is a bad thing, but it would keep things in here. So let's see what happens. This goes on for 4 billion years. I sped it up a little bit to make it, whoops, I didn't speed it up. Let's try that one more time. Come on, go. There you go. 4 billion years. Let's go. So the first thing that happens, you notice, is that the number of objects goes away really quickly. Crossing the orbit of a giant planet is bad. When the orbit is ejected, I remove it from there. You don't see it. Second thing you see is, notice that in this region, in the inner region where things are kind of green, all you see is that the orbits are turning. They're spinning like the hands of a clock, only backwards, I guess. That's that spinning that I told you about before. Everything spins around. Outside this region, though, you can tell you are being affected by this planet, and you start to see objects being captured into this region over here, like this. This one gets no, not this one. This one. No. This one gets captured. Nope. Maybe this one. This one. One's going to get captured. This next one. No. This one. No. No. Okay, there's bad news. The bad news is nothing gets captured over there. Everything that we thought was going to happen did not happen. We thought there was going to be a cluster of objects over here that were being captured. Nothing lives over here. And in fact, after 4 billion years, it's all over here. There are not a lot of objects left over here. Remember how many we started with? There were a ton to start with. But after 4 billion years, the only objects that have remained are over on the opposite side from where the planet is. We scratched our heads and thought, what do we do wrong? This can't be right. And then, of course, you do like you always do. It's like, we should have known this. It's obvious. It's obvious, right? It's obvious that if you have planets, well, you know how orbits work. Things spend most of their time out here, and then they go fast through here, and then most of their time out here, and then fast through here, most of their time out here. Same thing over here. Slow here most of its time, fast through here, slow most of its time. An object that's doing this spends most of its time out here. Planet 9 spends most of its time out here. These things stay most of their time close together. That's bad. They get perturbed and ejected. The only way to stay safe for as long as possible is to spend most of your time over here while the planet is spending most of its time over here. You still have to sneak through here really quickly and get out again, but you're doing it as fast as you can in the same place that the planet is doing as fast as it can. So you have the highest chance of surviving. Your chance of surviving is still pretty low. Not many objects have made it after 4 billion years. And if you came back another couple billion years later, there would be nothing left. The fact that we see anything in these objects, in these orbits, is luck that we're here at 4 billion years instead of 6 billion years after the sun. So the fact that there are these objects on these orbits that we found now we realize tells us that there has to be a planet on an orbit like this. And also that planet, I didn't show you this part, but that planet also has to be tilted the same way that the objects over here are tilted. This was pretty astounding. And we were still really, really uncomfortable with this idea because we just did not want to be the 36th and 37th astronomer to say, oh, there's a giant planet out there. Let's all go find it, and just be wrong like everybody else was wrong. And so we sat on it. We thought to ourselves, it's easy to come up with an observation and explain it. The observation being that there were these objects here like this, what's going on. It's a lot harder to make a prediction and have that come true. And we really wanted to come up with a prediction. There were a couple of interesting things. One is that we realized that this planet, we didn't even realize it at first, but this planet naturally pulls objects like Sedna out into the orbit that Sedna has. And so we didn't predict it, but it explained something we weren't trying to explain to begin with. That's good. That made us pretty happy that some weird thing about the solar system was explained in a way that we weren't trying to do. But we really wanted a prediction. There were two problems. We wanted a prediction. The other problem was one of the predictions that these computer models made was not coming true. The prediction that the computer model made was that there should be another set of objects, not just these ones on the opposite side of the planets, but there should be another set of objects perpendicular to the planet and the other objects on orbits perpendicular, but also tilted by 90 degrees in their orbit. So they looked like these funny wings. And I looked and we couldn't find any evidence that anything like this existed. And we were just about ready to give up and throw away our theory when I realized I had failed to look in all of the places at all the different objects in the outer solar system and all the data for reasons that are really stupid and just there's no good excuse for it, but I hadn't looked at them. And finally we found a new set of data to look at and realized there are objects on these tilted orbits. And we quickly sat down in my office and looked to plot them where we were and wanted to see if they were on these wings perpendicular. And the answer is you don't want to see that again. You want to see this, that these objects that are on these perpendicular orbits are exactly where we predicted them. There are these objects that are perpendicular to the plane of the solar system, perpendicular to where the planet and the other objects are. And moreover, these objects, there was no explanation for where they had come from. They'd been discovered over the past 10 years. I'd kind of not paid attention like I should have. And every time a new one was discovered, people scratched their head and said, I don't know where they came from. The answer is they come from Planet 9. Planet 9 very naturally makes these objects like this. Planet 9 makes these purple objects in orbits like this. It makes these blue objects orbits like this. It pulls orbits into orbits like Sedna's. It's a pretty good theory. We're now suddenly explaining three things, only one of which we tried to explain to begin with. And when we saw this, Constantine and I think both of us at that moment, our jaws hit the floor and we're like, oh, this went from sort of a cute project, can we explain this, to holy cow, there's really a planet out there. And I hate to be for us to be the 36th and 37th people to say this and then tell you that the first 35 people were all wrong, but the first 35 people were all wrong, and there really is a giant planet out there, and it needs to be found. What else can we predict? Well, there's one other prediction that we make, which is we will find more objects like all of these. And that's slow. It took about 15 years to find these. In the last 10 years, 6 years, we've been speeding up a little bit, and there are more now. And you can see that these are all the objects that are orbits beyond a certain distance. There is, and the yellow one is the planet itself. There is one object known in the wrong direction. And I will tell you, that's actually good, because our theory actually doesn't predict that 100% will be in one direction. There should be a small fraction that go in the same direction as the planet. And so we were getting a little worried that our theory was too good. But the predictions are that there should be objects over here. The objects are over here. All of our predictions seem to be working out. It is very difficult to explain what we know about the solar system today without the existence of a giant planet out there. So I am fairly sure that there is a giant planet to be found out there at the edge of the solar system. And I'm happy to be the 36th and or 37th person to tell you so, and to tell you that even though those other 35 people were wrong and crazy, we might be crazy, but I don't think we're wrong. So let me tell you what we know about this planet and how we know it. So one of the things we know, oh, actually there's one more, I forgot. We made another not prediction, but realization of something else that the planet did. And I forgot I put the slide on for you. Another really interesting thing that a planet does that we hadn't thought about until we started doing more computer simulations is, I'm going to show you orbits. Here's again, this is Uranus and Neptune orbit. Here's a random object that's on an eccentric orbit. Here is a planet. And I'm looking at one of these objects that is the cluster in this case. Remember, it's opposite the planet. So the cluster is over here. This is one of those objects that is not in the cluster. It's on the other side. And let's just watch it over time. Its orbit evolves because it interacts with the planet. Sometimes it's in the right direction. It's kind of circulating. It's not very nicely captured. Every time its orbit gets close to Neptune, though, it changes. So Neptune gives it a little kick, changes the orbit, but it's also being tugged along slowly by the giant planet. But occasionally, come close to Neptune. Let's see it. Boom, little kick. Sometimes Neptune doesn't just kick it outward. Sometimes it can kind of pull it in. Come on, Neptune, pull it in. It's random. It goes out sometimes, in sometimes. Sometimes Neptune can pull it in so much, it pulls it all the way in to the inner part of the solar system and gives you an object that is no longer a very distant object, but an object that has been pulled into the inner solar system, but on one of these crazy perpendicular orbits. Remember those objects that I showed you, the blue ones, were on these orbits that are perpendicular to the plane of the solar system. Neptune can sometimes pull them in, and we get more of these. Planet 9 puts these objects in very, very particular places and does not put them in other particular places. More importantly, nothing else known in the solar system can give you these perpendicular orbits. Again, this is something that was being discovered over the past 15 years. Nobody knew where they came from. Let me show you. Oops, I don't really want to show you that again. I'm going to show you a plot from a paper we wrote, so it's a little more detailed than you need to care about. But I'm going to show you the semi-major axis, the distance away from the sun of the object, versus its inclination. Inclination of 90 means that it's absolutely perpendicular. Inclination of 0 means that it's in a flat prograde orbit. 180 means it actually goes the wrong direction. Semi-major axis is one thing. Perihelion, the closest approach to the sun, is another. This is all the known objects, and they're all down here on very easily understood orbits. All of these objects, these little dots, have orbits that are understandable. They're just put in place by Neptune. Above this gray line, above an inclination of 60, notice that there are none of these little dots. No known planet can put objects above this inclination of 60, except for planet 9. But planet 9 doesn't put them everywhere. It puts them in where these green areas are. It absolutely does not put them in the white areas or very well in the gray areas. It puts them in the green areas, and there they are. They're just perfectly where you would predict them to be by planet 9, and perfectly not where you wouldn't put them to be by planet 9. I find this plot, it's a little detailed, and it's not one that I usually show. I don't give, for an utterly public talk of people who don't ever think about astronomy, I don't show this one, but I thought I'd show it just to you guys because I just find this astonishing. This is one of the most amazing predictions, I think, that Planet 9 does, is the very details of where it is. So I am really convinced there's something out there. So that's something out there. Well, we think it has a mass. We at first thought it had a mass of something like 10 times the mass of the Earth. It's an interesting mass because, in the solar system, we have Neptune and Uranus, which is 14.5 times the mass of the Earth. And we have Earth, which is precisely 1 times the mass of the Earth. And we have nothing in between. Well, at least we thought we had nothing in between. And yet, this in-between mass, this is the most common planet mass in our galaxy, if you look at other stars. And so I used to teach a class at Caltech, and I would always say, isn't it weird that we don't have a planet that's the most common mass? And the answer is, yeah, it would be weird, but I think we do have this planet. I think this is one of the most common types of mass that there is. We now know, and I'll show you in a minute why. It's probably not 10, it's probably closer to 6. And we got that through analysis of these detailed computer simulations. Something that's 6 times the mass of the Earth, well, in the picture here, it's sort of pictured as a scaled down version of Neptune. Could be a scaled up version of the Earth. We don't really know. Our guess, though, is that 6 times the mass of the Earth, if you look at other planets around other stars, that tends to be a miniature version of Neptune rather than a big version of the Earth. Incidentally, the fact that things around other stars tend to be miniature versions of Neptune, or even the size of Neptune, is one of those reasons that planetary decadal report that you guys heard about right before I talked, it's one of the reasons that people are interested in heading to planets like Uranus and Neptune, is to get a good look at what these more common types of things in the rest of the galaxy are like. Okay, so we think it's 6 times the mass of the Earth. What does that make it? Well, here are the planets that with their real sizes, not their cartoon sizes. So big old Jupiter, Saturn, much bigger than people give it credit for, because people always like to give pictures of Saturn with its rings. You have to make Saturn look smaller. Saturn's really quite huge. Uranus and Neptune, still pretty big. Mercury, Venus, Earth, Mars, definitely a huge step down. Asteroids, tiny, tiny, tiny. Here's all the objects that we know in the Kuiper Belt, really quite small. There's Pluto. If I took it away, you would not notice the difference. Eris, even more massive than Pluto. Planet 9, it's big. This is not slightly larger than Pluto. Let's all argue whether it's a planet or not. This is the 5th largest planet in the solar system, and a substantial mass still waiting out there to be found. So let's go find it. I'm just going to very quickly go through our attempts to find it and where we think it is. And we came up with predictions on where it is, basically by developing a new mathematical technique to compare these computer simulations that we did, like the ones that I showed you at the beginning. Compare these computer simulations with the detailed observations, with an understanding of where all the astronomers have been looking throughout the sky. You put it all into a big computer program that I'd spent 5 years working on, and 4 years working on and 1 year running, and you come up with this very simple plot after all these years, which is where Planet 9 is in the sky. This is the most, the other plot was the most amazing plot of prediction versus reality. This is my most amazing plot of just pure prediction. Here's where Planet 9 is in the sky. These maps are of the probability of finding it at any particular place. Okay, so this line, this is a a projection of the whole sky onto one plane. Here is the stellar equator. The ecliptic is this line through here. The galactic plane is between these two thick lines. Planet 9 is here. It's tilted by about 15 degrees to the ecliptic, as you saw before. Its most likely position is out here. And the reason it's most likely there is because it's on an elliptical orbit and it spends most of its time on the outer parts of elliptical orbit. This is the outer part of its elliptical orbit. So its most likely place, it's in the northern hemisphere, as you can see. It's in or close to the galactic plane. And as you'll see, it's even worse. It's probably in the galactic plane. Like if you could choose the worst place to be, well, you would pick the southern galactic plane. But the second worst place is the northern galactic plane. It's probably where it is. You can also, our theory predicts its distance. So its most likely distance is about 400, 500 AU in this position over here. But if it's in its closer positions, it could be as close as maybe 300 if it's over in here. And most excitingly, it predicts how bright it is. It predicts a magnitude. So its most likely magnitude is something like 21, 22, could be as faint as 24, 25, could be as bright as 19th magnitude. Somebody in this audience has a telescope that they can see 19th magnitude things with, I'm guessing. Anybody able to see 19th magnitude objects with their telescope? Yeah, so it is, but your telescope is probably not in the southern hemisphere. So sorry, bad news. You gotta be in the southern hemisphere to see it at 19th magnitude. Northern hemisphere, 20, maybe 20. So for crowds who don't know magnitudes, which is not you guys, I explain what all these magnitudes are. I'm going to skip the backyards, but remind you that, at 21st magnitudes, there are hundreds of telescopes that could see it. At 22nd, there are dozens. At 24th, it's a few of the largest ones. At 26th, it's really tough. Not impossible, but tough. So let's go find it. The way that we have been approaching this is to go from the bottom up, which is first rule out the brightest ones. So sorry, you're not going to be able to find it if it's 20th magnitude because we already ruled that out. So we went to my favorite telescope on the planet, which is the 48-inch Schmidt telescope at Palomar, which is right on the side of the 200-inch telescope. This is the telescope with which 20 years ago we discovered Eris and Sedna and all these things. These days, you don't get to sit on the chair in your chair and look through the eyepiece and smoke a pipe. Instead, a gigantic CCD mosaic sits right here and it takes pictures of the sky night after night after night as the Zwicky transient facility. And we analyze those data looking for Planet 9. So this is the same plot as before. It looks a little chunkier just because I'm using smaller samples to find it, but ignore the chunkiness. With the Zwicky telescope transient facility, we can see most everything up to about 20 and a half, at least in the northern hemisphere. So I'll just show you what we ruled out. All of these objects, you can see we kind of cut right down here. We didn't rule out down here. We can still 18th magnitude, southern hemisphere. Anybody want to move to the southern hemisphere? Do me a favor, go look down there. It is not any of these. Okay, so that's telescope 1. Telescope 2. The dark energy survey. The dark energy survey is being done, was done with the 4-meter telescope in Saratololo. And they did a huge survey of the sky. It looks kind of like a tank. And part of their survey of the sky covered where Planet 9 should be. This is our predictions of where Planet 9 should be. Sadly, they only cover a small chunk of Planet 9 space. I really wish I could move their survey over just a little bit to cover the right spot. But they at least covered that spot right there and they didn't find it. So you can take that and rule out that chunk. You can see their little spot was right here. So it's not there. It's not there. It's not here. Let's keep going. My favorite telescopes. Well, you can see 4 of my favorite telescopes in this one picture. One of them is not that one. It's actually that one over on Haleakala. This is Mauna Kea. In the background is Maui, and Haleakala has the Pan-STARRS survey, which is a telescope about the same size as the 48-inch telescope that we just looked at, but it's doing a deeper survey and ruling out stuff. And we are 96% finished analyzing the Pan-STARRS data. I have a few parts of the particularly the southern galactic plane, which are still processing. But I think we're not going to find it. And so we go from this to pan-stars. Notice we have ruled out a lot of space in through here. The southern galactic plane, boy, this is towards the center of the galaxy. There are a lot of stars in through here. It's painful. We're having a hard time in through here. And there's this little strip. We don't have anything in the south. So again, 18th, 19th magnitude. Anybody want to pick up their telescope and go to the southern hemisphere? There's a little left. So our final big survey, we got to get this chunk right through here. This chunk in through here, it's 22nd magnitude to 24th magnitude. That is the sweet spot for, Keck telescopes, which are my babies. The Subaru telescope. The Subaru telescope is, of course, the Japanese national telescope on Mauna Kea, and it has this amazing camera at the top of it. This amazing camera at the top, way up there. This is an 8-meter telescope. That is a huge camera up at the top. There's me and Constantine. You can tell he's a theorist. He's having to breathe oxygen up there at 14,000 feet. Real astronomers don't breathe oxygen. We just let ourselves get stupid instead. But this big camera at the top we are doing our final survey to cover that region where, fingers crossed, we are hoping to find this planet in this region in through here. We're analyzing the data still. We've covered most of it. It's slow going in through the galactic plane. But that's where it's most likely to be. So that's where we're looking. So it's nice to see these plots. I like to look at it instead as, where's Planet 9? Well, Planet 9 is, you can actually see it on this beautiful picture. Everybody's favorite constellation, Orion. I challenge you to pretend like it's not your favorite constellation. I know it is. Don't fool me. You can see Taurus right here, this cosmic battle. The path of Planet 9 goes right between Orion and Taurus, and right into the galactic plane. You can see the density of stars getting high in through here. This is the galactic plane. Planet 9 is probably right up in through here on top of Orion's head. Every time I go out and see the sky and see Orion, I just kind of stare at that region of the sky because I can just kind of feel this thing out there. I am strongly convinced it's there, and I think that's where it is. So I do want to end though with a good note of skepticism. Is it really there? Are we just being fooled? I gave a talk last week to a group in New York, and somebody asked me a perfectly reasonable question, which is, if you keep looking and don't find it, when are you going to be convinced that it's not there? And I think the answer to that question is when there's a better explanation. Right now, Planet 9 is an amazing unifying explanation for 4 or 5 disparate phenomena in our solar system, which otherwise have no explanation whatsoever. And doesn't mean it's true. Maybe somebody will come up with another unifying explanation. Maybe there are 5 separate explanations. But until these things are explained, it's hard for me to explain the solar system without the existence of Planet 9. So that is not to say that it is the only thing that will ever be able to be out there, but it has been 6 years since we proposed the existence of this planet, and there really are no viable explanations that have been put forward since then. And astronomers are usually pretty good at coming up with something. So I am skeptical that somebody will be able to come up with another explanation. And I think the only solution then is that there's a planet out there and that the other 35 people were wrong and we're right. And we just have to go find the thing. If we don't find it with the LSST survey, I gave away the answer. If we don't find it with the Subaru survey, I have high hopes for the LSST, the Vera Rubin Observatory, coming up soon. And we're even, if in case it's fainter than we expected, a little further away than expected, we're actually working with some people at JPL on a crazy gravitational probe that we think would be able to find it by putting satellites in orbit around the Earth, Mars, and Venus, and doing continuous range finding between the 3 of those and seeing the gravitational pull. That's another crazy story for another day. But we have hopes. I think we're going to find it. And I will end finally where I started with this great poster stolen from the Plan 9 from Outer Space movie. I gave a talk to my students last week on Planet Nine, and I showed this poster and I asked them if anybody had ever heard of Plan 9 from outer space. 0 of them had ever heard of Plan 9 from outer space. I predict that probably almost every single one of you have heard of Plan 9 from outer space. Is there anyone who has not heard of Plan 9 from outer space? Okay, good. So widely famous as the worst movie ever made, at least. I look at Wikipedia. It's true. I'm not making this part up. But it's Ed Wood. Ed Wood, of course, is a genius director. It's 1959. He makes this crazy movie about alien invasion and zombies and Vampira and Bela Lugosi. And it's insane. The movie's insane. You can actually watch it on Wikipedia. I challenge you to actually sit and watch it on Wikipedia. But 1959, Ed Wood, he's a genius. He's a mad genius, and he knew things that nobody else knew, even in 1959. So I love on the poster this little graveyard scene where they're digging up a zombie, and if you zoom in, this thing that Ed Wood put in there, which is there it is right there, R.I.P. Pluto in 1959. Even Ed Wood knew. So thanks. I'm glad to have had this chance to talk to you guys. Thanks for sitting through all of it. And I don't know what your general plan is, but I'm happy to answer some questions for a little bit if you guys have them.
Mike, I have a question. Actually, I have a comment. So now apparently Plan 9 from outer space is now only the 5th worst.
What?
Yes.
God, what are the 4 other ones?
There's a documentary, I can't remember if it's on Netflix or on Amazon Prime, about the 50 worst movies ever made.
I'm sad to hear that. I actually, it was good while it lasted.
Having seen Plan 9 from outer space, especially when Bela Lugosi died, and I think it was the dentist was pretending to be him.
Yeah.
It says a lot.
Yeah. It's legitimately bad, and people are like, oh, it's so bad that it's good. It's like, oh no, it's so bad that it's really, really bad.
It's an exercise in patience. That's
yes.
My question is, so what you talked about tonight was explaining these perturbed orbits of these small objects. What perturbed Planet 9?
It's my favorite question. Okay, so I started this whole story with Sedna, right, which was on this crazy orbit that's elliptical and pulled away from the planets. And I was like, aha, we have an explanation for Sedna. It was done by Planet 9, which is elliptical and pulled away from the planets. Don't tell anybody. So who put Planet 9 there? I don't know, is answer 1. But answer 2 is, I think it's the explanation that we originally had for Sedna. We do believe that the Earth, the sun was formed in a cluster. And so I think the Planet 9 originally formed in the Uranus-Neptune region. That's such not a weird explanation that is now the generally accepted theory of the formation of the solar system is that we had an extra ice giant to begin with, and that it got ejected. And I think that when it got ejected, we were still in the cluster of stars that we were formed in, and it got injected, perturbed by those stars, and became Planet 9. Doesn't have to be true. But it's a very natural explanation for both the orbit. The size is about the right size for an ice giant that didn't quite get big enough because it got ejected a little too quickly, and the orbit that it currently has. It is not impossible that it was captured from another star. So a star comes by the sun, it had Planet 9, we steal Planet 9 and eject the star. That works. The probability is not high, but it's not 0. And the third possibility that I don't think is true, but we've been fooled before, is that maybe it actually formed there. I told you at the beginning that you have to form in circular orbits. What do I know? Maybe you can form in a slightly elliptical orbit, and or maybe you form in a circular orbit and that cluster perturbed you. Again, the probability seems low, but it's not something I would completely discount until we can learn more about what the real orbit is and what the real nature of Planet 9 is. So I'm looking forward to discovering it so we can actually then start to learn these things. I'm going to answer Jack O'Neill in the chat. Says, can the telescopes in space be used to look for Planet 9? So all of our favorite telescopes in space, Hubble Space Telescope, James Webb, so awesome. Not good for searching. The reason they're not good for searching is because, I showed you that camera on the Subaru telescope, which is bigger than the mirror on the Hubble Space Telescope. The telescopes in space tend to not have very big detectors. They're usually designed to look at small areas of the sky in great detail rather than huge areas of the sky. So HST and JWST will be fantastic for studying Planet 9 in detail once we find it, but not great for doing it. An answer, I think I see hands in the audience, so somebody's gonna have to take over that part for me. I'm gonna do one more from the chat, which was, have you included any nearby stars in your simulation? Not yet. We're doing that right now because we're worried that they may sort of change things around a little bit and our answers are a little simplistic, but we're doing that now. So somebody call on people in the audience and tell me.
Bruce, yeah.
Yeah, what about the southern observatories like Atacama? Have there been surveys of the, cover huge areas of the southern sky?
So there's a survey. There's only one really good all sky southern survey, which is the Sky Mapper survey out of Australia. And those data are not quite released publicly yet, but we are eagerly awaiting getting our greasy fingers on them. And then we'll with luck, we will either find it or rule out those parts of the southern sky. Sky Mapper doesn't go particularly deep, but Planet 9's, when it's closest to the sun, when it's at perihelion, it's in the southern part of the sky, so it's brighter there. So we should, and that whole big chunk of sky in the southern galactic plane, I think we should be able to rule out once the Sky Mapper data, or find it. I always say rule out because it kind of feels like all I'm doing these days, but maybe we'll find it.
Kathy,
2 questions.
speak loud.
What's the orbital period that you predicted for Planet 9?
So it's a tough one because you saw that there was a pretty wide range of where it could be. So I would say between 5,000 and 15,000 years. So we have a best fit with an uncertainty on it, and that encompasses kind of that range.
Okay, I have another question, and I'm not sure how to ask it because when Pluto was eliminated as a planet, there was a definition of what a planet was. And if memory serves, I thought it was a somewhat circular orbit.
No, so let me talk about planet definitions, but with the caveat first. The IAU planet definition is dumb. Let's just all acknowledge it.
Well, that's confirmed.
So it has nothing to do with Pluto or not Pluto. It's just a stupid definition. It's a perfectly fine concept. I would even say that the idea that the IAU should have written down a lawyerly 3-part definition of the word planet is itself dumb. We in astronomy, we don't work in definitions. There's no definition for star or galaxy or blah, blah, blah. We work in concepts, and the concepts are really very clear. They were trying poorly to convey the concept, but they made the mistake of turning it into a definition. And so now it's a 3-part lawyerly definition. And once you have 3-part lawyerly definition, you get lawyers involved in whether things are planets or not, which is about the last thing you want in the world. But then let me say what their 3-part lawyerly definition has to be in orbit around the sun. It has to be round, and it has to have cleared its orbit. It has to be round, not the orbit has to be round. The object itself has to be round. All they're trying to say by the clear its orbit part is that it's the dominant gravitational mass in its vicinity. So Planet 9 fits those definitions, even though it's a dumb definition. You certainly see it. You saw in that simulation. It cleared the heck out of its orbit. There are a few more objects left. It's not quite as fast at clearing its orbit as other things, but it's doing a job pretty quickly. Clearly it's round because it's the 5th largest thing out there, and it's in orbit around the sun. So even the very silly 3-part lawyerly definition, it fits. But more importantly, it fits the concept of what we mean when we say the word planet. When we say the word planet these days, we mean the dominant gravitational bodies at every distance in the solar system. And Planet 9 dominates the outer solar system from just beyond the edge of Neptune all the way out to its orbit. It is actually, in many ways, the most planety of all the planets that there is out there in its dominating sense.
I have one more question. I remember in the 90s, there was an object, I don't know if it was a Kuiper Belt object or an Fourth Cloud object named or
Quar. That was not 90s. That was 2002. I discovered that. It's one of my babies.
well, obviously it's stuck. I mean,
Yes.
so, yeah. So explain that or describe that object.
So Quar was one of the first of the sort of getting to be larger and larger objects that we were discovering in the early 2000s when we started the survey. I showed you that 48-inch telescope at Palomar in the very early days of CCDs on telescopes. So if you remember, the early 2000s was when we were first getting our handheld digital cameras, and those handheld digital cameras, you remember those first ones when you were pretty excited because you had a 400 by 600 format, and then you got a megapixel, and then you got 10, and it was so exciting. And we astronomers were the same way. So we put together one of the first really large detectors that we could use. In the past, astronomers too. The first CCD I ever used was 800 by 800. I think it was huge. At the time, and then we got the 1K by 1Ks in the late 1990s, and by 2000 we started putting together. We had a 2K by 4K, and we got 112 of them. And we kind of glued them all together with bubble gum and baling wire and put it on the back of this telescope. And we went from being able to look at about this much sky all at once to this much sky all at once. It was the most exciting thing in the world. And it took us about 5 years to cover the whole sky, searching for bright Kuiper Belt objects. And the Quar was the first of them that we found. So in many ways, it's one of my favorite of my little babies. It's about a third the size of Pluto. It's that's about half the size of Pluto. It's an interesting mix between, we saw all these nice pictures of Pluto and its moon Charon, and Pluto is all icy with methane and colors, and Charon is all just like pure water ice with craters. And Quar is probably this interesting mix between the two, on a very circular orbit, but tilted by about 6 degrees compared to the plane of the solar system. It's got a tiny little moon around it. Quar itself is named after the Tongva tribe of Native Americans who are native to the Los Angeles basin here when I lived. So we actually called them up when we discovered it and asked them if we could name it Quar, and they changed the name for it, the spelling. So we now use their separate spelling. And when we discovered the moon around it, we actually called them again. We're like, hey, we found a moon. Why you guys just named the moon? So the moon is named Waywoot, which is the force that sang and danced Quar itself into existence. So it's just been this fun connection with. So because we discovered it here, we were like, we want to name it after something relevant to mythology of the Los Angeles area. So Quar, it's one of my favorite little ones. It's kind of like your children; they're all your favorite when no one else is listening. So I'll say now that Quar is one of my favorites.
Thank you.
Dave,
Yeah, I know that you told us that you feel that this is your best explanation. What other objects have you tried to put in your simulations that didn't quite work or that didn't work, and why?
So any single object, the only way to have a single object be responsible for everything you see is something like what Planet 9 is. So the other things that we tried that didn't work, the first thing we tried is we thought maybe it's not a single object. Maybe all of these objects that are clustered the way they are, maybe there are so many of them that they're holding themselves together due to gravity. Remember, the first clue that we had that something was going on is that these things were all lined up instead of moving apart like they should have moved apart. But maybe they held each other together. So we did a lot of computer simulations of trying to do that, and it just doesn't work. Every time they came close to doing it, Neptune would break them apart again. So that doesn't work. We tried things like the overall pull of the Milky Way galaxy. We tried crazy dark matter ideas. We tried everything we could think of. I can't even think of all the other ones we did again, but anything that we could think of that would exert some sort of gravitational force, we tried doing this, and none of it worked. This was the only one that we can really get to make any sense. That's stable, that works and stays in place for a long period of time. You can kind of fake things to make it work for a second, if and then promise, to look away and it won't work again. But that's all we got. Kind of boring and mundane. We're just like the dude from 1846 who's like, oh, it's got to be a planet. Like, seems like we could have come up with some better explanation after all these years, but I think it's got to be a planet.
Thank you.
Question, would it be possible, I know you talked about James Webb not being really a suitable instrument, but to look at this, but in the infrared, wouldn't it be easier to pick up something that's that far away because it's going to be so cold?
Yeah, actually, so yes, absolutely yes. Infrared could end up being a much better way of looking for it. And in fact, even better than infrared might end up being radio wavelengths, because the problem is, as you get further and further away, so the sunlight has to get there, and that it gets fainter by 1 over the distance squared, inverse square law that you all remember, and then it has to get back. So that's another 1 over r squared. So it's 1 over distance to the 4th. So you make something twice as far away, and suddenly you're 8 times fainter. That is tough. It's tough to look at reflected sunlight. Something that's emitting heat, well, it's a little bit colder when you move it further away, but not that much colder. So it's only 1 over r squared. So if it gets far enough away, or if you're looking for something even further than Planet 9, infrared or radio wavelengths get to be possibly a better solution. The problem is, we are so much better at building wide field cameras in the optical wavelengths than we are in the infrared. We haven't, we need a mute there. We're so much better at optical wavelengths, building these big cameras, that we're still haven't caught up. We are going to catch up soon in the radio, though. So some of these big radio telescopes that are built for surveying the cosmic microwave background are actually quite suitable for finding Planet 9 also. So if we fail to find Planet 9 in the next couple of years, this may be the way to go. Although I like our crazy gravitational idea better because it's more fun and crazy and modern.
Thank you.
Any other questions?
Oh, there's one on, let's see, how will we celebrate Mike how will you celebrate Mike when you confirm the existence of the planet? I could go to Disneyland. That's what you do, right? I don't know. I'm going to celebrate by being incredibly busy, because we have as soon as we discover it, then the fun parts start, which is learning about it. We have what we call day zero projects. Day zero projects are things we are planning on doing the second we find it. Imaging it with HST to see if it has moons, to see if we can get it in mass, getting a spectrum of it with the Keck Observatory to see what the surface is made out of, looking at it with JWST, looking at it with the ALMA telescope and the Atacama. So there will be no celebrating. That's when the real work begins. So it'll be celebrating by working hard, which I can't wait.
Good. All right. I guess that's all the questions.
Thank you so much.
Thanks, Mike.
All right. Thanks for taking your evening, everyone. It was fun.
We topped out around 40 participants between YouTube, Zoom, and in person. That's a good meeting.
Awesome. Awesome.
And
All right.
there are more than one astronomy club represented, by the way.
Excellent. All right. Good night, everybody.
Thank you.
Thanks.
Thank you.
Thanks so much.